Let's move on to the second important topics in today's lecture, which is the matrix multiplication. Previously, we talked about linear transformation, which, by the way, is one of the most important operations that we can do in any linear algebra. The second important thing that we can do is the matrix multiplication. Now, what we learned from the previous discussion, the linear transformation, that you can think about matrix multiplication as applying one transformation. So if you use a matrix and you multiply that with the vector, you're essentially transforming that vector and moving that vector somewhere else, right? So what does the meaning of a matrix multiplication or matrix to matrix multiplication mean geometrically, and what fundamentally it entails, right? So that entails that when you're doing matrix multiplication, you are essentially applying one transformation and then you're again applying another transformation together. Or in other words, you are concatenating different transformations, or in other words, you are composing and creating a composite transformation which is composed of two different matrices. Okay. So you're taking the first transformation and then again doing second transformation, and you can do a sequence of transformation by doing a sequence of matrix multiplication by multiplying different matrices together, and that is the geometric meaning of matrix multiplication, and that's the intuition behind why matrix multiplications are important. They allow you to compose different transformation together. So let's try to understand this concept first of all numerically, and then we will try to get into the geometric intuition just using the 2D problems that we have. So let's say we have these two matrices, and if you want to multiply them together, right, we can go through a simple calculations, and that will, the output of this multiplication could be written. So what does this multiplication represent? First, it defines a type of transformation, something that we have discussed, and this is the same matrix that we have used actually in the previous discussion of vector matrix multiplication or the linear transformation aspect. So here we will essentially take the unit vectors, and unit vectors will get here, and the y which is right here will get twisted here. That transformation will be there, and then we will have another transformation of that unit vector which will be represented by this clockwise rotation. So what it will do, it will basically rotate a 90 degree, right? It will rotate it 90 degree, and that's the second operation. So when you're multiplying them together, the resultant matrix will be affect in such a way that you will have the first transformation and then you will rotate it again, and that is the composition that happens when you're doing this matrix multiplication. And again, I will revise or give you more context of what is actually happening using some geometric examples that we have, right? So here, once you multiply, if you do simple arithmetic, you will get a final matrix like this. But this matrix, the resultant matrix, will be such that if you take the initial one, both the operations have been imbibed in this matrix itself. So what it will do is will take I, it will make bigger, and then rotate it back and bring it back here. That is encapsulated by this matrix multiplication. But how do we arrive at this final matrix? This is multiplication of this. So essentially we are doing this two transformation, first this transformation and then second transformation on top of that. That is being also represented compositely in a single matrix right here. Okay. So what we get out of matrix multiplication? We get a resultant transformation which could be constitutive of multiple different steps, multiple different transformations that we have. And this resultant matrix that we get by multiplying these individual matrices that we have is called composition matrix. Okay, and then the effect that you will get is if you take this individual multiplication and go through that sequence, wherever the final vector will arrive, if you take the initial vector and multiply by this matrix, you will arrive at the same final vector. So let's see these operations in a geometric sense. Okay, so we have this. Let's see numerically how this is computed. So what we do is we take this overall first matrix and we multiply that with the first column that we have, and we can split it up, and we have this sort of operations. From this we can sum that up, and so essentially this will lead to 2, 0. Similarly, we'll take the matrix on the left hand side and then take the second column of the right hand side matrix, which is minus 2, 1, bring them here. Then we can break it further, and then we can have this simple calculations. 2 minus 2 is multiplied by the first column, and then minus 1 is essentially multiplied by the second column, and we have an output. Now we take this 2, 0 and minus 1 and put them together in a single matrix, and that's the output of the matrix multiplication. So this is a simple 2 by 2 matrix multiplication that we have constituted, and this is the composite matrix or composed matrix, which is output of the matrix multiplication we have seen here. So this is how we numerically implement, and there are numerical formulas that you can generalize. Rather than having this example, you can generalize this formula, and you can use this formula, and you can write a code which will does a matrix multiplication for you. Okay, so in general, what happens, if I just want to summarize this in this equation term, this will be a 2 by 2 example, simple example that I'm trying to put. You will output a composite matrix which will be given by this equation. So the elements of the matrix, first matrix is Wx, Yz, and the elements of the second matrix PQ and Rs, and if you multiply them together, then the first element will be given by this equation Wp plus Yq and so on, right? So this is the equation that you can directly write, and essentially that will imbibe all the steps that you're doing, but rather than going through this kind of thing, you can sum them up in one way, and you can be shorter if you write this general formula. So let's take this example a little bit further and try to understand what is happening geometrically. So we have understood the numerical implementation, and you might have come across the numerical implementation of matrix multiplication, but I think it's also useful to have some geometric intuition behind matrix multiplication. Okay, and as we talked, it's basically composing multiple different transformation on together. Okay, and again, overall effect, if the initial matrices are a linear transformation, then your overall matrix composition will be also a linear transformation. Okay, so let's say what is happening when we are composing multiple different matrices through the matrix multiplication idea in the geometrical sense. So let's say we take the same example that we are taking, right? This is the first transformation that will be carried out by the matrix on the right hand side, and then we will have a second transformation which will be carried out by the matrix on the left hand side. Okay, and so let's focus on what this first transformation is doing, right? And recall that when last example that we carried out when we were discussing with the linear transformation, we had I here and j was here, but after applying this transformation, the unit vector I moved from this location to this location right here. And the unit vector j, which was right here, after this transformation was transformed this, and then we got a different grid, and now in this grid we can represent all the vectors that was there in the original grid. Okay, now let's see what happens when we apply this second transformation on top of that. Okay, so when we are applying second transformation, what is going to happen? We are taking I, which was here, right, and we are basically converting that and moving it 90 degree here, because that it is multiplied by 1, 0. So I will come here, it will move here, and j will move here. I was right here, it will rotate by 90 degree and it will come here, and that is what is represented by this transformation T1, T2. Okay, so when we are doing this matrix multiplication, we are typically moving from right to left, right, and there is a sequence that we need to follow to understand what is the sequence of transformations that are happening. Okay, so again, if we have a vector that we are multiplying to the this composite matrix which is coming out of multiplication of T1 and T2, then typically the vector will be on the right hand side. We will first do T1 V1, so that will be the first transformation, and whatever the result of that will be then transformed by this T2, and that will output what is the location of V1 as a result of these two different transformations T1 and T2. Okay, so let's see how this works. Basically, it transforms from right to left, and it's essentially similar to what you do function composition. If you're doing function composition, you will take a function g, and then whatever is the transformed function, you will compose that in function x. So it's similar to function composition. It's a matrix multiplication is basically transformation composition. That's the way to understand this concept. Okay, so let's see how this intuition works and what this geometrically means. Okay, so the process of transformation is same. Okay, so let's take this same example. We have this vector first. What we did, right? This vector was located here, and this is the initial starting point where I was unit vector in this, j was unit vector in this, and we have this parallel grid which was perpendicular to each other. Now if once we apply the first transformation, we basically move the I to here, j to here, and the transformed vector moved here, and this is something that we derived in the linear transformer lecture. Now let's take the second composition, which is the geometric intuition that I want you to have, is to take all this three composition together. Now what happens? You took the previous transformed axis. So if you see, this one is right here, and what you will do is this is the I vector, you will apply this 0 minus 1 on top of I, so it will basically rotate and it will come on this direction. And you will take this j and it will rotate by 90 degree and it will come along this direction, and that is what you will see what is happening to the unit vector. So you saw from this I came here, from here the j was rotated by 90 degrees. So this is what is happening to the unit vectors by applying this transformation T1 and then applying this transformation T2, and similarly, the vector that was there after first transformation here will get transformed and will be located here. So that's what is represented by all the transformation, composite transformation that is happening there. Okay, so what we are doing from initial location, right? We are moving first transformation, we are getting here from the initial location, which is represented by this case right here. We take the first transformation, we move here, and in this transformation both the unit vectors are getting transformed and the vector v is also getting transformed. And then we take the second transformation matrix, we are multiplying that. In that sense, again the unit vectors are getting transformed, and then the vector is also getting transformed. So you think about, sequential operation of different transformation, and composing this transformation is essentially what is the geometric meaning of how to understand the matrix multiplication in general. Okay. Now recall this matrix, essentially what it does, it basically rotates things by 90 degree in the clockwise direction, and this is one of the important things that you see in many geometric application. If you have to do certain rotation, you have very specific types of matrices that you can use for transformation. Okay. So again, let's take this example and again go through it. So in the transformed coordinate, after all this transformation, what has happened? The final location of the transformed vector after multiplication with this matrix and again multiplication with this is right here. Now what we do? We find out the coordinate of this transformed vector in the original coordinate system. So you can see here is -2 and 5 units, and that's why you will have 5 in x and -2, and that will be the final location of the vector after composition of two transformations T1 and T2, which are defined by two different matrices.